Good morning, dear students. I am Bhavesh, Assistant Professor, Computer Applications Department, International School of Management, Patna. As per the part of ISM TV on Operating Systems and UNIX, today's my topic is CPU scheduling algorithms. We will be talking about what CPU scheduling algorithms are, how they work, what are the benefits, and since it is targeted for BCA students, we will also be talking about what you should know in order to have questions, queries, and what will be important things related to university exams, right? So the first CPU scheduling algorithm, in fact, the simplest one is first come, first serve. As the name suggests, the process which arrives into the ready queue first will be served first. This is the basic criteria, or you can say this has a priority, and the priority is who is coming first, right? So for example, if we take three processes, P1, P2 and P3, all having burst times written over here. For example, for P1, the burst time is 24 milliseconds. Normally, burst times, we talk in terms of milliseconds. It could be even lesser than that, but for our understanding, we take millisecond as the burst time unit. So for P1, it is 24 milliseconds, P2 is 3 milliseconds, P3 is 3 milliseconds. Right? Now, the thing which is important to understand here is the first thing, what is the purpose of this particular CPU scheduling algorithm and how it works. The second is what information you need if you are being given with a question that these are the processes and this is the CPU scheduling algorithm to be used, how they will be scheduled. Then what information you will require about those processes. Third, how to prepare Gantt chart for those processes. Next would be what would be the average waiting time of all the processes and what would be the waiting time of individual processes. This all we will be talking about for each of these CPU scheduling algorithms, right? So as the name suggests, first come first serve, it means the one which comes first into the ready queue will be scheduled on the processor first, right? So here P1 has arrived first into the ready queue with 24 milliseconds as burst time. So you can see the Gantt chart. It started from 0th millisecond and it has gone till 24th, and all these time it was occupied on CPU. So P1 has finished its execution. Soon after that, P2 will be scheduled on the CPU for 3 milliseconds, and then P3 will be scheduled on the CPU for 3 milliseconds, right? So total execution time was 30 milliseconds, whereas if we talk about waiting time for each individual processes, then for P1 it was 0, because as soon as P1 arrived into the queue, it was scheduled on the CPU, right? So as soon as it has reached into the ready queue, it was scheduled on CPU. It basically didn't wait even a single millisecond for CPU to be allocated. So the waiting time for P1 here I have mentioned as 0. Now for P2, when we consider the time when P1 was executing on CPU, entire time P2 was waiting. So P1 has executed for 24 milliseconds. In that case, P2 was waiting for 24 milliseconds. So P2's waiting time would be 24 milliseconds. Then P2 has finished its execution. P3's turn had come. P3 again executed for 3 milliseconds, right? So P3 was waiting till the time P1 and P2 has finished. P2 finished at 27th millisecond. P3 was waiting till that. So waiting time for P3 would be 27 milliseconds. Now if we want to calculate average waiting time, it would be sum of waiting time of each individual processes divided by total number of processes. So 24 plus 27 divided by 3, because for P1 there was no waiting time at all, right? So that way the average waiting time was calculated as 17 milliseconds. Now there is a catch. The thing is, FCFS is being known to give highest waiting time in most of the cases. But again, the waiting time, the average waiting time as well as the waiting time for each of the processes may vary depending on how the processes are arriving. I mean to say, what is the sequence of those processes to arrive. Here I have given, I have just changed the sequence. Same processes, same burst time, but I have just changed their sequence, the order in which they have arrived into the ready queue. So in this case, first P2 has arrived, then P3, and then P1. So basically what I have tried to show over here is the process having less burst time has arrived first, and the one which has highest burst time has arrived in the last. Right. So in that case, it's our common sense to understand that the processes will have to wait for lesser time. So in fact, the waiting time for each of the processes will be less as compared to the previous case. And of course, the average waiting time also will be reduced. And here I have shown that the average waiting time has become 3 milliseconds, right? Now, the next one is shortest job first scheduling. Shortest job first scheduling, it is, in this, processes are being scanned for their burst time. The one which has the least burst time will be scheduled on the processor first, right? It doesn't depend on the order. In which order they have arrived into the ready queue, it doesn't matter. The thing which matters is which process has the least CPU burst time. Which process requires the least amount of time to be executed on the processor. That will be scheduled first on the processor to be executed. Now there can be a situation when there could be multiple processes in the ready queue which requires same amount of time. Maybe suppose there are 5 processes and process number 2 and process number 4. They both require only 3 milliseconds to be executed on the CPU in order to finish their execution. In such cases, how to identify which one requires the shortest time, right? We can't differentiate because both requires similar amount of time. So in that case, we use first come first serve basis for those processes, those who are having similar burst time requirement, right? So here, if you can see, I have taken 4 processes in this example and their burst times are also mentioned. Here, P4 has the least burst time requirement, that is 3 milliseconds. So first of all, as you can look at the Gantt chart, here process P4 was scheduled first at time 0, and for 3 milliseconds it has executed. If you leave away P4, because P4's execution got over, after P4 we have P1 which has the least burst time, that is 6 milliseconds. So soon after P4's execution, P1 was scheduled on the CPU and P1 was executing for another 6 milliseconds. So total 9 milliseconds have elapsed. Now if you leave away P4 and P1 and if you consider only P2 and P3, P3 has least requirement of burst time, so 7 milliseconds. After P1, P3 has executed for 7 milliseconds. After P3, P2 has executed for 8 milliseconds. So now if we look at the waiting time for each of the processes individually, here we can see in case of P1, P1 was waiting for 3 milliseconds for P4 to finish. So the waiting time for P1, individual waiting time for P1 would be 3 milliseconds. Same way, if we look at P2, P2 was waiting for 16 milliseconds because before P2, P1, P4, P1 and P3, all these 3 have executed, which took 16 milliseconds, and for all those 16 milliseconds P2 was waiting. So waiting time for P2 is 16 milliseconds. For P3 in the same way it is 9 milliseconds. But for P4, P4 didn't require to wait even for a single millisecond. So P4, it was 0. Now I have just added all these waiting times. There were 4 processes altogether. So I have divided them by 4 and the average waiting time has come out as 7 milliseconds. Now, here there could be two situations. It is called as preemption, which we would have also seen when we have talked about the different stages of processes. That a process from one stage can be preempted to another stage. It cannot happen for all the stages, but yes, there are some particular stages from where the process can be preempted to another stage. So here, when we are talking about SJF, it could be preemptive or it could be non-preemptive also. Now, what is preemptive and what is non-preemptive, that we should understand, right? Now, when it comes to non-preemptive, just imagine like for this example itself, there were four processes. They were executing, they were into the ready queue, and based on their smallest burst time, they were getting allocated with the CPU to get executed. Now, if it is preemptive, we are talking about if it is preemptive, what will happen, how the execution will happen. Now just imagine P1, P2, P3, P4, all these four are there in the ready queue. As per this data, P4 has the smallest burst time, so P4 has got allocated with the CPU. P4 has started its execution. It executed for 1 millisecond, and soon after that, another process P5 has arrived into the ready queue, whose burst time requirement is only 2 milliseconds. It means, now if you look at all the processes in the ready queue, P5, the one which has arrived just now, has the least burst time requirement. So ideally, this should be provided with the CPU to get executed. But actually, the CPU is already occupied by P4, because the time when P5 entered the ready queue, P4 was already allocated with the CPU, right? So if it is preemptive, what will happen in that case? As soon as P5 has entered into the system, P4 will be preempted again back to the ready queue. It means it will be forcibly asked to stop and will be moved to the ready queue, so that CPU is being made available for the current process which has arrived, P5, with the least burst time as 2, right? This is preemptive. If it was non-preemptive, then what would have happened? In that case, P4 was allowed to complete its execution for 3 milliseconds. So as soon as P4 has finished, now we would be having P1, P2, P3, as well as P5 with 2 milliseconds as burst time. So now it would be the turn of P5 to get allocated with the CPU, and P5 would have got executed, right? So here, in case of non-preemptive, forcibly the CPU would not have been deallocated for any of the processes. But in case of preemptive, the CPU is being deallocated forcibly so that the process which has higher priority could be executed on the CPU, right? So this was all about preemptive and non-preemptive. Here I have given the example as well. So when we are talking about preemptive scheduling, in that case, we also require to know at what time the processes have arrived into the ready queue, right? So if you look at this, P1, P2, P3 and P4, we also require their arrival time. Earlier, whatever we have discussed, in those we were talking about only the process IDs as well as their burst time. But when it comes to preemptive scheduling, in that case, we will also need to know at what time the process has arrived into the ready queue, right? Now, looking at this, P1 has arrived at 0 time. I mean, the time when CPU became available, P1 was already there inside the ready queue. So CPU is not meant to be waiting. In that case, P1 was allocated with the CPU, irrespective of looking at whether other processes are there, because in fact there were no more processes inside the ready queue at that time for getting executed on the CPU. So P1 was allocated with the CPU. Its burst time requirement was 8 milliseconds. But again, what happened is P2 entered into the system. I mean, P2 also entered into the ready queue, but its arrival time is 1. It means by then P1 has already executed for 1 millisecond, right? So since it is primitive, we are talking about primitive, and as I told you that in case of primitive, as soon as a higher priority process, here the priority is the CPU burst time. So if the higher priority process arrives, the process which is currently executing on the processor will be forcibly taken back to the ready queue, and the CPU will be made available for the new process which has arrived with higher priority. So here what has happened, look at the Gantt chart. P1 has executed for 1 millisecond, and then P2 has arrived at first millisecond. P2 was made available with the CPU, and P1 would have got preempted into the ready queue. P2 has executed for 4 milliseconds because its requirement was 4 milliseconds, and 4 milliseconds means total 5 milliseconds have elapsed. By then, on second millisecond, P3 has arrived into the ready queue. On third millisecond, P4 has arrived, right? So all these have already arrived into the ready queue by then. Now P2, as soon as it has finished its execution, it has come, the turn of P4 has come, because even if you look at the remaining burst time requirement for P1, it would be 7 milliseconds, which is higher as compared to 5. So P4 will be scheduled on the CPU. Once P4 has finished, now we have only P3 and P1 in the system. P1 requires 7 milliseconds. So P1 has got scheduled on the CPU, and then P3 has got scheduled on the CPU for 9 milliseconds. This way, all the processes have got executed, right? Now here, when we are finding out average waiting time, we will have to be little cautious, because in this case, we also have to consider at what time these processes have arrived into the ready queue, right? So if you look at this, I have mentioned here 10 minus 1. 10 minus 1 is the waiting time for, P4, right? 10 minus 1 is the waiting, P1, here we have written the waiting time for P1. So P1, as soon as it has entered into the system, it was allocated with the CPU first. It executed for 1 millisecond, right? But then it was preempted. When it was preempted and it was there inside the ready queue, it was just waiting for the CPU. So it was waiting from millisecond 1 till millisecond 10. It means for 9 milliseconds it was waiting. That's the reason I have mentioned here 10 minus 1, right? And then for P2, P2 has arrived at millisecond 1, and it got CPU also at millisecond 1 only. It means it didn't wait even for a single millisecond, right? So 1 minus 1. Now coming to P3, P3 has arrived into the system, into the ready queue at millisecond 2, and P3 got CPU at millisecond 17. It means it has waited for 17 minus 2 milliseconds, right? So that's what I have mentioned here. Then coming to P4, P4 has arrived into ready queue at millisecond 3, and it has got the CPU at millisecond 5. It means 5 minus 3. It waited for 2 milliseconds. Now add all of them. There are 4 processes. Divide by 4, and whatever result has come, that is the average waiting time of this particular primitive SJF scheduling. And at last, I have also mentioned that primitive SJF can be called as shortest remaining time first scheduling, because that is what we have noticed here. P1 executed for 1 millisecond, and remaining burst time was 7 milliseconds for them, for that particular process. So whenever the CPU, whenever the scheduler was scanning the processes for getting allocated on the CPU, it was considering their burst time. But in case of P1, it was considering their remaining burst time, right? So that's the reason we call it as shortest remaining time first scheduling also. Next is priority scheduling. Now, first we should understand what is priority. Priority we can consider as a kind of value, a kind of integer value, which tells or which gives an information that in which order this particular process will be scheduled on the CPU for execution, right? So normally the priorities would be 0 to 7 or 0 to 4095. However, on any operating system, whether 0 or 1 is the highest priority or 10 is the highest priority, that varies. And if you are writing any kind of program based on CPU scheduling algorithm for priority based scheduling especially, in that case you will have to refer to the guidelines of the operating system, maybe the details of the operating system, to understand how the priority values are being used on that particular operating system, whether they consider 1 as the highest priority or 10 as the highest priority, right? Now, if suppose multiple processes with same priority arrives into the ready queue, then again, to break the tie, we will be using FCFS. Here I have given an example where I have 5 processes, their burst time, and as we are talking about priority based scheduling, the priority is also mentioned, right? So now the process which has the highest priority, in this case I have considered the least priority value as the highest priority. So 1 means highest priority, 5 means least priority. So P2 has highest priority, P2 has the priority as 1. So first P2 was selected and P2 has got scheduled on the CPU for execution. It executed for 1 millisecond because its burst time was 1. And then next would be P5 because its priority is 2. So P5 has got allocated with the CPU. It executed for 5 milliseconds. And then P1, whose priority is 3, has got scheduled on the CPU. After P1, P3 has got scheduled on the CPU because its priority is 4. And then at last P4 has got scheduled on the CPU because its priority value is 5, right? So in this case, again, we can find out what is the waiting time for each individual process. Average waiting time also, we can add all the waiting times of each of the processes, divide them by total number of processes, and that would be the average waiting time. Again, priority scheduling can also be preemptive or non-preemptive, as we have discussed earlier. But again, here there could be a problem. A problem is of indefinite blocking. Just imagine we are talking about preemptive priority scheduling. There is a process whose priority is 5. And it means it is meant to be executed in the last, right? Now, since it is preemptive, imagine that the process with priority value as 1 has got executed, 2 has got executed. Again, another process has arrived into the ready queue, which has priority value as 1. Again, P3 has got executed. Again, another process has got entered into the ready queue with priority value as 1 or highest priority. So in that case, there could be a situation when the process P5, whose priority value is 5, will never get a chance to get executed on the CPU. So that is called as indefinite blocking, or it will be starving for the CPU, right? And there is a solution to it, which is called as aging. In this case, what happens is, over a small time period, the priority value of those processes which are, being identified as being starving, their priority values are being increased by certain numbers so that they can get a chance to get executed at some time, right? I hope all these 3 kinds of CPU scheduling algorithms are clear, right? In the next video, we will meet with the remaining CPU scheduling algorithms. Till then, thank you. Have a good day.